All right, so far we have talked about pulmonary ventilation, okay, breathing air, the mechanisms in which we take air in and out. We've talked about pulmonary diffusion, so gas diffusion between the capillary blood and the lungs. We've talked about how we transport oxygen and CO2 in the blood. And the last thing we're going to talk about is capillary diffusion. Okay, so capillary diffusion is like pulmonary diffusion. It's the diffusion of the gases, but instead of between the lungs and the blood, we're talking about diffusion of oxygen and CO2 between the capillary blood and the tissues. And for us, the primary tissue that we're talking about is muscle tissue. Alright, so this is mostly going to be a review of things we've already talked about. Capillary diffusion is the exchange of gases at the tissues, or for us, the muscles. And as we've talked about throughout this chapter, the reason that the gases move in the direction that they do is because they move down the pressure gradient. They move from an area of high PO2 to low PO2, or high PCO2 to low PCO2. The other thing I want to point out is that the amount of oxygen that's taken up is going to be proportional to oxygen use, right? So if the PO2 in the muscle is going to be affected by how much PO2, how much oxygen the muscle's using, right? So we have a PO2 out here in the capillary, and the PO2 in the capillary is higher than the PO2 in the muscle, and that's why oxygen is moving out of the capillary and into the muscle. During exercise, when you use more oxygen, you're going to get a drop in the PO2 in the muscle. Okay, so if it's being used more, then the amount inside the muscle is going to be lower, and therefore P2 is going to be lower, right? And if P2 is lower, then P1 minus P2 is bigger, setting up a bigger pressure gradient and more uptake. Okay, so it all makes sense. Same thing is true for CO2, but everything is in the reverse direction. So CO2 removal from the muscle is going to be in proportion to CO2 production. Okay, because if you're, let's see, alright, so now if we're talking about CO2, we've got a PCO2 in the capillary, we have a PCO2 in the muscle, and this is P2. Oh no, actually it's the reverse, right? This is P2, and this is P1, okay? Because the CO2 in this capillary blood that's coming in from the arteries is relatively low, because we got rid of the CO2 in the lungs. And it's relatively high in the cells and in the muscle, because that's where we're producing CO2. So now we've got a reverse gradient. P1 is going to be the PO2 in the muscle. P2 is going to be PCO2. P2 is going to be the PCO2 in the capillary, and therefore this is going to favor CO2 leaving the muscle and going into the capillary. Okay? And when the muscle is working, it's producing more CO2, so when the muscle is working, we have a higher PCO2, which means we have a higher P1, which means P1 minus P2 is higher, okay, which means we have a bigger pressure gradient, which means more CO2 removal. So removal is going to be proportional to production, because production affects P1. Okay, so similar to what we see with the oxygen, same concept. Also keep in mind that when the muscle is working, not only are we producing CO2 in metabolism, right? Actually, this deserves a page. Okay, so we've got okay, so through aerobic metabolism we're producing CO2, but also when the muscle is working, it's also producing more lactic acid than it does when it's not working, and so we're getting hydrogen ions, and what this does is it causes hydrogen ions to bind with bicarbonate ion and produce CO2 and water. Okay, so remember that we've got this equilibrium. If we add hydrogen to this equilibrium, this reaction is going to shift to the right, and when that happens, we produce CO2. Okay, so CO2 removal is going to be proportional to production, and production around a working cell is going to come both from the aerobic metabolism within that cell and also the buffering of the lactic acid from that cell. Okay. AVO₂ difference, we've already talked about this. So AVO₂ difference is the difference in oxygen concentration between the arteries and the veins, and it reflects how much oxygen is being taken up by the tissues. Okay. So at rest, and you should remember this figure because we've already talked about it. At rest, we have a typical oxygen content in the blood of about 20 mils of oxygen for every 100 liters of blood. If you're curious about where that number comes from, the average person has about 15 grams of hemoglobin in every 100 milliliters of blood. Remember, men have about 14 to 18, women have about 12 to 16. So on average, if you average men and women together, we have about 15 grams of hemoglobin per 100 milliliters of blood. I haven't told you this yet, it's not super important, but every gram of hemoglobin, if it's fully saturated, it can carry 1.34 milliliters of oxygen. So if you do the math here, the result is 20 milliliters of oxygen in every 100 milliliters of blood. And we see that at rest, and we also see that during intense exercise. Okay, because remember that saturation stays high. You're not losing hemoglobin during exercise, so there's no reason why the amount of oxygen in the arteries would be any less during exercise. So maybe less at altitude, maybe less with lung disease, but for our purposes it's going to be the same even during exercise. And then what we see in the veins is that we, at rest, is that we say 15 to 16 milliliters of oxygen. So let's just go with 15. If the oxygen in the veins was 15, that would mean that the AVO₂ difference was 5, right? 20 minus 15 is 5. And so what that's telling us is that the cells are taking up 5 mils out of 20. Okay? And 5 out of 20 is about 25%. Okay? So at rest, your body is taking up about 25% of the oxygen. During heavy exercise, okay, we're left with 5 in the vein, which means we took up 15 out of 20, which means we took 75%. Okay? So the point I'm trying to make here is that 2 points. One is that when we exercise, we take more oxygen out of the blood. AVO₂ difference goes up. and it goes up from something like 25% to something like 75%. But it's interesting that even with intense exercise, we're not taking all of the oxygen out of the blood. Okay, there's still oxygen in the veins, and there's still oxygen in the blood that ends up back in the lungs. Okay, it's not 100%. The last thing I want to talk about here is once the oxygen is unloaded in the capillary blood and it gets into the muscle cell. Okay, so we had hemoglobin let go, oxygen went into the muscle. Okay, when it gets into the muscle, it gets picked up by myoglobin. Okay, myoglobin similar to hemoglobin. The role of myoglobin is that it binds and transports oxygen within the cell. And what it does is it picks up oxygen at the cell membrane and carries oxygen and drops it off at the mitochondria, where we can then use it in the electron transport chain to be that final electron acceptor. Okay?